In 2008, a team of NASA scientists pointed a satellite at 800 galaxy clusters scattered across the sky and found something that should not exist. Every single one of them, spread over a volume of space so vast that light takes more than 3 billion years to cross it, was drifting in the same direction. Not randomly, not toward any structure anyone could see. They were all streaming together at somewhere between 600 and 1,000 kilometers per second toward a patch of sky between the constellations Centaurus and Vela. Think about that speed for a moment. 1,000 kilometers per second is roughly 2.2 million miles per hour. At that velocity, you could cross the entire diameter of the Earth in about 13 seconds. You could travel from the Earth to the Moon in 6.5 minutes. And this was not one galaxy, not one cluster, but hundreds of the largest gravitationally bound objects in the universe, all participating in the same coherent motion, like leaves caught in the same invisible current, in a river that should not exist. The man who found the signal called it dark flow, not because it had anything to do with dark matter or dark energy, though both of those enigmas would later become entangled in the story, but because whatever was causing it was invisible. It could not be any object or structure within the observable universe, because the flow extended far beyond the gravitational reach of anything astronomers had ever mapped. The implication was immediate and unsettling. If nothing inside the observable universe could explain the motion, then the source had to be outside it, something beyond the cosmic horizon, beyond the farthest point from which light has had time to reach us in the 13.8 billion years since the Big Bang, was pulling on everything we could see. To understand how extraordinary this claim is, you need to appreciate what galaxy clusters are. They are not small things. A single galaxy cluster can contain hundreds or thousands of galaxies, each with hundreds of billions of stars, all bound together by gravity within a halo of dark matter that outweighs the visible galaxies by a factor of 5 or more. A typical massive cluster has a total mass of 10 to the 14th to 10 to the 15th solar masses, meaning 100 trillion to a quadrillion times the mass of the Sun. These are the largest gravitationally bound objects in the universe, the nodes of the cosmic web, the places where the filaments of dark matter and gas that span hundreds of millions of light years converge and concentrate. And Kashlinsky was saying that hundreds of these colossal structures, the heaviest things that exist, were all being carried in the same direction by something no one could see or explain. This is a story about a measurement that most cosmologists believe was wrong, a theoretical prediction that came true before the data existed. A satellite that was supposed to settle the argument and instead made it worse, and a new experiment designed by the same man who started the whole controversy, now mounted on a European space telescope 1 million miles from Earth, which might finally answer the question within this decade. The question is simple to state and staggering in its implications. Is the universe being pulled in a direction it should not be? And if it is, by what? The scientist at the center of this story is Alexander Kashlinsky, and his path to dark flow began about as far from NASA as you can get. He was born in 1957 in Riga, the capital of what was then the Latvian Soviet Socialist Republic. The space age had just begun. Sputnik launched that same year, and Kashlinsky later said the timing was fitting because space was all he thought about growing up. What actually ignited his obsession with astrophysics was not Sputnik, but a science fiction novel by the Polish writer Stanislaw Lem called The Magellanic Cloud, about humanity's first voyage to another star system. The boy in Soviet Riga read that book and decided he would spend his life trying to understand the universe at the largest scales. He studied physics at Latvian State University from 1973 to 1976. But the Soviet Union was not a place that encouraged independent scientific ambition, and in the late 70s he emigrated to Israel. He finished his bachelor's degree at Tel Aviv University in 1977 and a master's by 1979, then moved to Cambridge, England, where he earned his PhD in astrophysics under the supervision of Martin Rees. This is the same Martin Rees who would later become the Astronomer Royal, one of the most distinguished cosmologists alive. Kashlinsky's thesis was on the formation of bound systems in the expanding universe, essentially asking how gravity manages to pull things together in a cosmos that is flying apart. It was the perfect training for the question that would define his career decades later. In 1991, he joined NASA's Goddard Space Flight Center in Greenbelt, Maryland, as a senior staff scientist, and he has been there ever since. The tool that made dark flow possible was not any telescope on the ground. It was the Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001 to map the cosmic microwave background with unprecedented precision. The CMB is the afterglow of the Big Bang, a bath of microwave radiation that fills all of space at a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. It is the oldest light in the universe, released roughly 380,000 years after the Big Bang, when the primordial plasma cooled enough for atoms to form and photons to travel freely. Every point in the sky glows with this ancient light, and the tiny variations in its temperature, measured in millionths of a Kelvin, encode the density fluctuations that eventually grew into galaxies and galaxy clusters, and the entire cosmic web. Kashlinsky was not using the CMB to study those primordial fluctuations. He was using it as a backlight. Imagine shining a flashlight through fog. If the fog is stationary, the light passes through with a predictable pattern of scattering. But if the fog is moving toward you, the scattered photons get a slight boost in energy. Moving away, they lose a little. The same principle applies to the CMB and galaxy clusters. Galaxy clusters are filled with intracluster gas heated to tens of millions of degrees, hot enough that the electrons in that gas are moving at a significant fraction of the speed of light. When CMB photons pass through this blisteringly hot gas, they scatter off the free electrons and gain energy. This is the Sunyaev-Zel'dovich effect, named after the Soviet physicists Rashid Sunyaev and Yakov Zel'dovich, who predicted it in 1970. The thermal version of this effect depends only on the temperature and density of the cluster gas, and it distorts the CMB spectrum in a characteristic way that astronomers have measured many times. But there is a second, much subtler version if the cluster itself has a bulk velocity relative to the CMB rest frame, meaning it is moving through space above and beyond the general expansion of the universe, then the scattering electrons impart an additional Doppler shift. This is the kinematic Sunyaev-Zel'dovich effect, or KSS, and it does not distort the CMB spectrum. It simply shifts the entire blackbody curve up or down in temperature by a tiny amount that depends on the cluster's speed along the line of sight. A cluster moving toward us compresses the scattered photons slightly, making that patch of the CMB a fraction of a microkelvin warmer. A cluster moving away stretches them, making the patch cooler. The effect is described by a deceptively simple equation. The temperature change divided by the background temperature equals negative tau times V over C, where tau is the optical depth of the cluster, roughly 1% for a typical massive cluster. V is the peculiar velocity, and C is the speed of light. For a cluster moving at a few hundred kilometers per second, the temperature shift is roughly 1/1,000,000th of a Kelvin. That is far too small to measure in any individual cluster. Buried under the much larger thermal SS signal, primary CMB fluctuations, instrumental noise, and foreground contamination from our own galaxy's dust and synchrotron radiation. This is where Kashlinsky's cleverness came in. He and Fernando Atrio Barandella, a theoretical physicist at the University of Salamanca in Spain, had developed a statistical technique back in 2000. Atrio Barandella's path to this collaboration was itself unlikely. Born in the Canary Islands, he studied physics at the University of La Laguna before earning his PhD and moving to Berkeley for postdoctoral research, eventually settling at the University of Salamanca, one of the oldest universities in Europe, founded in 1218. His specialty was the statistical analysis of CMB data, and he brought a rigor to error estimation that would prove critical in the battles to come. The idea they developed was simple in concept and brutal in execution. Take the WMAP temperature map. Identify the positions of hundreds of known galaxy clusters using X-ray catalogs, because the same hot gas that produces the SSE effect also glows in X-rays, making galaxy clusters among the brightest objects in the X-ray sky. At each cluster position, measure the CMB temperature in a small aperture after filtering out large-scale fluctuations and the thermal SE contribution. Any individual measurement is dominated by noise. The KSZ signal from a single cluster is like trying to hear a whisper in a hurricane. But if you stack all the measurements, random motions cancel out. Clusters moving toward us produce tiny cold spots. Clusters moving away produce tiny hot spots. And if those motions are truly random, pointing in all directions with no preferred orientation, the stack averages to zero. Nothing emerges from the noise. But if there is a coherent bulk flow, a current carrying all the clusters in roughly the same direction, the stack will not average to zero. Instead, it will reveal a net dipole pattern, a systematic temperature difference between one side of the sky and the other. Clusters on the side of the sky toward which the flow is directed will be systematically blue shifted, producing a slight cold excess, while clusters on the opposite side will be red shifted, producing a slight warm excess. The amplitude and direction of this dipole encode the velocity and direction of the bulk flow. It is a beautiful technique because it turns an unmeasurable individual signal into a statistical detection by exploiting the one thing that distinguishes coherent motion from random noise: correlation. To build the cluster catalog for the initial analysis, Kashlinsky recruited Harold Eberling, an astronomer at the University of Hawaii who had spent years compiling the most comprehensive X-ray surveys of galaxy clusters in the sky. Eberling is one of those quietly essential figures in astronomy whose work enables other people's discoveries. His massive cluster survey and its extensions based on the OROSAT All-Sky Survey X-ray data provided the coordinates and X-ray luminosities for hundreds of the brightest, most massive clusters, carefully vetted to remove spurious detections and contaminating sources. Dale Kochevsky, then a postdoctoral researcher at the University of California at Davis, helped assemble and cross-reference the catalog, ensuring that the cluster positions were accurately registered to the WMAP sky maps. Together, the four of them, Kashlinsky, Atrio Barandella, Eberling, and Kochevsky, applied the stacking technique to about 700 clusters using WMAP's 3-year data release. The dipole appeared at 3 to 4 sigma significance. It pointed toward a region near galactic coordinates L equals 290, B equals 30 degrees, in the direction of Centaurus and Vela. The implied velocity was between 600 and 1,000 kilometers per second, and it extended to at least 300 megaparsecs, which is roughly 1 billion light years. To put that distance in perspective, the nearest large galaxy to the Milky Way, Andromeda, is about 2.5 million light years away. The Great Attractor, the most famous gravitational concentration in our cosmic neighborhood, is about 150 to 250 million light years away. Kashlinsky was claiming a coherent motion extending 4 to 7 times farther than the Great Attractor, with no sign of falling off. When the paper appeared in September 2008 in the astrophysical journal Letters, it landed like a depth charge. The title was deliberately technical, a measurement of large-scale, peculiar velocities of clusters of galaxies, results, and cosmological implications. But the implication was anything but technical. If the measurement was correct, something was pulling on the largest structures in the observable universe from beyond the cosmic horizon. The cosmological principle, the foundational assumption that the universe looks the same in every direction on the largest scales, was in trouble. The reaction in the astronomical community was split in a way that revealed a deep fault line about how to treat extraordinary claims. Some researchers were genuinely excited. Bulk flows had been a subject of intense study for decades, and the measurements had always been limited to relatively local volumes within a few 100 million light years, where the inhomogeneity of the universe makes large flows expected. Nobody had attempted anything like what Kashlinsky was claiming, a coherent flow measured at cosmological distances, using the CMB itself as the measuring device. If it held up, it would be among the most important observational discoveries in a generation, evidence that something beyond our cosmic horizon was pulling on everything within it. Others, including some of the most prominent names in the field, were skeptical from the start. The KSSE effect had been discussed for decades, but successfully measured for individual clusters only in a handful of cases, each requiring exquisite control of systematics. The idea of extracting a statistical bulk flow from hundreds of noisy measurements, each individually consistent with zero, required an enormous leap of faith in the stacking technique, a method where subtle biases in the input catalog, the foreground subtraction, or the aperture choice could produce spurious signals that mimic a coherent dipole. The reaction was swift and sharply divided. Some cosmologists were fascinated. Lee Smolin, the theoretical physicist known for his work on loop quantum gravity and his critiques of string theory, called it potentially one of the most important observations in cosmology. Others were dismissive. The conventional view was that the signal was almost certainly a systematic error or a statistical fluke, because the alternative, that something beyond the observable universe was exerting a measurable gravitational pull, was too radical to accept without extraordinary evidence, and the evidence, while intriguing, fell well short of extraordinary. 3 to 4 sigma in a measurement with poorly understood systematics is suggestive, not conclusive. Kashlinsky told NASA's press office, "We never expected to find anything like this." He called it dark flow because, he explained, the prefix dark had become cosmology's way of labeling things whose source is unknown. Dark matter is matter we cannot see. Dark energy is energy whose nature we do not understand. Dark flow is motion whose cause we cannot identify. The name stuck, partly because it was evocative and partly because it captured the genuine mystery of the result. Within 2 years, the team doubled down, using WMAP's 5-year data release and expanding the cluster catalogue to roughly 1,400 objects. Now with Alistair Edge of Durham University added to the team, they published a follow-up in March 2010. The dark flow persisted. It extended to at least 800 megaparsecs, about 2.5 billion light-years, and the velocity remained roughly constant across 4 distance shells. That last detail was crucial and worth lingering on. In standard cosmology, bulk flow velocity is expected to decrease on larger scales as the universe averages out to homogeneity. As you survey a larger and larger volume, the random peculiar velocities of individual clusters and superclusters average out, and the net bulk motion should converge towards zero. This is a direct prediction of inflation and the cosmological principle. But in Kashlinsky's data, the flow velocity at 2.5 billion light-years was just as strong as at 1 billion. It showed no sign of convergence. That is exactly what you would expect if the source lay beyond the observable universe entirely, because the gravitational gradient from an external source would be nearly uniform across the entire observable volume, producing a constant tilt at every distance. The 2010 paper also reported that the dark flow direction was consistent with several other known large-scale motions, including the direction of the CMB dipole and the Shapley supercluster, but extended far beyond the range where those structures could exert any gravitational influence. And the team's internal cross-checks showed that the signal was robust against changes in the cluster catalogue, the CMB frequency channels used, and the filtering procedures applied to remove foregrounds. They were confident. The cosmological community was not. But before we get to the battle over the measurement, we need to understand why this result was so disturbing to begin with. Because the strangeness of dark flow is not just that galaxy clusters are moving too fast. It is that the universe specifically promised this could not happen. The entire architecture of modern cosmology is built on the idea that at the largest scales, space has no preferred direction. And if that idea is wrong, then the foundations of the standard model of the universe are shakier than anyone wants to admit. The reason dark flow should not exist comes down to a single event that happened in the first trillionth of a trillionth of a trillionth of a second after the Big Bang: cosmic inflation. In the early 1980s, a young physicist named Alan Guth, working at the Stanford Linear Accelerator Center, proposed that the universe underwent a brief period of exponentially accelerating expansion when it was about 10 to the minus 36 seconds old. In a time span so short that no human metaphor can capture it, a region smaller than a proton ballooned to a volume larger than the entire observable universe today. The expansion factor was at least 10 to the 26th, and possibly far larger. Inflation was originally conceived to solve specific problems with the standard Big Bang model. Why is the universe so geometrically flat? Because inflation stretched any initial curvature to undetectable levels. The way inflating a balloon makes a small patch of its surface look flat. Why is the CMB temperature so uniform across the sky, even between regions that have never been in causal contact? Because before inflation, those regions were in contact, sharing the same temperature, and inflation stretched them apart faster than light. These are the flatness problem and the horizon problem, and inflation solves both of them elegantly. Why are there no magnetic monopoles, the exotic topological defects that grand unified theories predict should have been created in abundance in the early universe? Because inflation diluted them to undetectable densities, pushing them beyond the cosmic horizon. And perhaps most impressively, inflation predicted that the primordial density fluctuations, the seeds of all the structure we see today, should follow a nearly scale-invariant power spectrum, with a slight red tilt, meaning slightly more power on large scales than small. This prediction was made in the early 1980s, and the WMAP and Planck satellites confirmed it with extraordinary precision 3 decades later. Inflation is not just a speculation, it is one of the best tested ideas in all of cosmology. But inflation does something else that is directly relevant to dark flow. Before inflation, the primordial universe might have had all kinds of large-scale structure, gradients, irregularities, preferred directions. Maybe one side was slightly denser than the other. Maybe there was a gravitational tilt across the whole thing. Inflation was supposed to erase all of that. When you stretch a patch of space by a factor of 10 to the 26th, any pre-existing gradient gets diluted to insignificance. If there was a density slope of, say, 1% across the pre-inflationary patch, after inflation that slope would be spread across a volume so enormous that within the observable universe, it would be completely undetectable. The observable universe in this picture is a tiny homogeneous bubble within a vastly larger post-inflationary space, and within that bubble, there should be no preferred direction of motion at scales above a few hundred megaparsecs. Think of it this way. Imagine you have a swimming pool with a slight tilt so the water is a centimeter deeper on one end than the other. Now imagine expanding that pool to the size of the Pacific Ocean while keeping the same 1 centimeter difference. The tilt would still technically be there, but it would be spread across 15,000 kilometers. At any point in the ocean, the surface would appear perfectly flat. That is what inflation does to the universe. Whatever structure existed before inflation, whatever gradients or preferred directions the primordial patch might have had, get diluted to undetectable levels within our observable volume. And this is why dark flow is not just another anomalous measurement. It is a direct challenge to one of the most successful and well-tested theories in all of physics. If there is a coherent bulk flow spanning billions of light years, either inflation did not dilute pre-existing structure as thoroughly as predicted, or something outside the inflated volume is exerting a force that inflation cannot account for. Either way, the simplest versions of inflation are in trouble. This is the cosmological principle, and it is not just a philosophical assumption. It is a prediction of inflation, and it is confirmed by observation after observation. The CMB is uniform to 1 part in 100,000. The distribution of galaxies at large scales follows a pattern that, when averaged over volumes larger than about 300 megaparsecs, looks the same in every direction. The expansion rate of the universe, as measured by the redshift of distant supernovae, appears isotropic. Everything we see says the universe has no preferred direction. So when Kashlinsky reported that hundreds of galaxy clusters spanning billions of light years were all streaming toward the same point, the reaction was not merely, "That's unexpected." It was, "That violates the fundamental prediction of the theory that underpins modern cosmology." Either the measurement was wrong, or inflation did not work the way everyone thought, or something outside the observable universe was exerting a force that should not be possible. Now, the obvious first question is whether known structures could explain the motion. Because the universe is not perfectly smooth. It has lumps, enormous concentrations of matter that pull on their surroundings through gravity, creating what cosmologists call peculiar velocities. These are motions superimposed on the overall Hubble expansion, and they are completely expected. Every galaxy has one. The Milky Way itself moves at about 631 kilometers per second relative to the CMB rest frame, and we know the sources of most of that motion. The most famous is the Great Attractor. In 1986, a group of 7 astronomers, who inevitably became known as the Seven Samurai, published a landmark study of the motions of elliptical galaxies across the sky. The team was led by Donald Lynden Bell, one of the most brilliant and eccentric astrophysicists of the 20th century, a man who had already made foundational contributions to the physics of accretion disks around black holes and the dynamics of the Milky Way. Lynden Bell was a quintessentially British scientist of the old school, trained at Cambridge, fond of classical languages, and possessed of a physical intuition that his contemporaries found almost uncanny. He had predicted in the 1960s that the centers of galaxies should harbor supermassive black holes fed by spiraling gas, work that would eventually be vindicated by observations and honored with numerous prizes. Together with Sandra Faber at the University of California at Santa Cruz, one of the most influential observational astronomers of the 20th century, along with David Burstein at Arizona State, Roger Davies at Cambridge, Alan Dressler at the Carnegie Observatories, Roberto Televich at the Royal Greenwich Observatory, and Gary Wegner at Dartmouth, Lynden Bell developed a new method for measuring galaxy distances using the relationship between the brightness, size, and velocity dispersion of elliptical galaxies. This method, now called the dn sigma relation, allowed them to estimate each galaxy's true distance independently of its redshift, and therefore to map the peculiar velocity field across a large volume of space. The pattern that emerged was unmistakable. Everything in our region of the universe was streaming toward a single point, converging on a direction the team named the Great Attractor. Lynden Bell named it the Great Attractor, a deliberately dramatic term for a gravitational concentration that no one could see directly because it sat almost exactly behind the plane of the Milky Way, in the zone of avoidance where our galaxy's dust and stars obscure the view. The Great Attractor sits at about 150 to 250 million light-years from Earth, in the direction of the constellations Norma and Triangulum Australe, centered on the Norma cluster. Its estimated mass is on the order of 10 to the 15th solar masses, which sounds enormous until you realize that it accounts for only about 44% of the Milky Way's peculiar velocity. Even the most massive nearby structure cannot fully explain why our galaxy is hurtling through space at over 600 kilometers per second. If you have heard that we are being pulled toward the Great Attractor and imagine some single irresistible force dragging our galaxy inexorably through space, the real picture is more complicated. The rest of our motion comes from even larger structures. The Shapley supercluster, lying at about 650 million light-years in roughly the same direction, is the most massive concentration of galaxies in the nearby universe, containing over 8,000 galaxies with a total mass exceeding 10 to the 16th solar masses. That is 10 quadrillion times the mass of the Sun. Shapley contributes another, roughly 30% of our local bulk flow. And in 2017, Yehuda Hoffman, Helene Courtois, Brent Tully, and Daniel Pomerade identified the dipole repeller, a vast supervoid in the opposite direction from Shapley, whose absence of matter creates an effective gravitational push, repelling galaxies away from it. Between the pull of Shapley and the push of the dipole repeller, our local motion is fully accounted for. Here is where you might think you have the answer to dark flow. Maybe Kashlinsky was simply detecting the pull of the Shapley supercluster and its neighbors, but he was not. And the reason is scale. The Great Attractor is about 200 million light-years away. Shapley is about 650 million. The dipole repeller is about 750 million. These structures explain bulk flows on scales up to about 150 megaparsecs, and they are entirely consistent with the predictions of the standard lambda CDM cosmological model. Lambda CDM predicts that the one-dimensional root mean square bulk velocity should be about 110 kilometers per second at 50 megaparsecs, and it should decrease on larger scales as the universe smooths out. At the 300 to 800 megaparsec scales Kashlinsky probed, the predicted bulk flow is essentially negligible, a few tens of kilometers per second at most. Kashlinsky's dark flow was 600 to 1,000 kilometers per second at those scales, 3 to 10 times the lambda CDM prediction, and it pointed in roughly the same direction as the Shapley supercluster, which initially seemed suspicious, but the flow extended far beyond Shapley's gravitational reach. At 2.5 billion light-years, you are 4 times farther away than Shapley. The gravitational influence of even 10 to the 16th solar masses drops off dramatically at those distances. There simply is not enough mass in the observable universe in the right configuration to produce a coherent flow of that magnitude at that scale. So the giant structure explanation fails. And this is what made dark flow so provocative. It was not a small excess over predictions. It was an enormous one. And it persisted across distance scales where no known gravitational source could operate. The first obvious escape route that Kashlinsky was simply detecting the well-understood pull of local superclusters was closed. Whatever was causing this motion, if it was real, had to be something else entirely. But maybe the measurement itself was the problem. The kinematic Sunyaev-Zel'dovich effect is extraordinarily difficult to detect, and WMAP was never designed for this kind of analysis. The potential for systematic errors, foreground contamination, and statistical flukes was enormous. Within months of the original paper, the critics arrived in force. The most important early objection came from a graduate student. In 2009, Ryan Keisler then at the University of Chicago, published a brief but devastating reanalysis of Kashlinsky's method. The key issue was the assumption of independence between WMAP's 8 frequency channels. Kashlinsky's team had used multiple channels to separate the KSCZ signal from the thermal SC effect and other foregrounds, treating the channels as providing independent measurements. Kessler pointed out that the channels share significant correlated noise from the CMB itself and from instrumental systematics. When you properly account for those correlations, the statistical significance of the dark flow signal dropped from 3 to 4 sigma all the way down to about 0.7 sigma, not even 1 sigma, consistent with noise. That same year, Stephen Osborne and colleagues demonstrated something equally worrying. They showed that if the thermal Sunyaev-Zel'dovich effect was not perfectly subtracted from the data, the residual contamination could produce a spurious dipole signal mimicking a bulk flow of 2,000 to 4,000 kilometers per second. In other words, the very foreground that Kashlinsky was trying to remove could, if imperfectly removed, create exactly the kind of signal he reported. Still, these were methodological critiques, not independent measurements. They showed that the detection could be an artifact, not that it definitely was. What was needed was an independent measurement with better data. And by 2013, that measurement arrived from the most powerful CMB satellite ever launched. The Planck satellite, operated by the European Space Agency, observed the microwave sky with far superior angular resolution and frequency coverage compared to WMAP. Planck had 9 frequency channels spanning a wider range, better control of systematics, and lower noise. In Planck Intermediate Results 13, published in 2014, the Planck collaboration applied the same KSE stacking technique to the positions of galaxy clusters from the meta-catalog of X-ray detected clusters, using more than 1,000 objects. The result was stark. The measured average radial peculiar velocity was 72 plus or minus 60 kilometers per second, consistent with 0. The 95% confidence upper limit on any bulk flow was 254 kilometers per second, several times below Kashlinsky's claimed 600 to 1,000. Princeton's David Spergel declared that the Planck paper appeared to rule out the dark flow claims entirely. A lot of coverage at the time said Planck had disproved dark flow. That is actually an overstatement, and here is why. Fernando Atrio Barandella did not accept the result, and his counterargument had genuine technical substance. Remember, Atrio Barandella was the error analysis specialist who had co-developed the KSS stacking method with Kashlinsky years earlier. But he occupied an extraordinarily uncomfortable position in this debate because he was simultaneously a member of the Planck collaboration itself. He had access to the data, the pipelines, and the internal discussions. He knew the instrument's strengths and its weaknesses from the inside. When he published his rebuttal, he was criticizing his own collaboration from within, arguing that the flagship result of one of the most expensive scientific instruments in European history had gotten its error bars wrong. In the collegial but fiercely competitive world of large scientific collaborations, this kind of public dissent takes real courage. It meant signing his name to a paper that implicitly accused dozens of his colleagues of a methodological error. It meant attending collaboration meetings where his analysis was the elephant in the room. And it meant risking his professional relationships for the sake of what he believed was a correct statistical assessment. He published a detailed response paper arguing that 2 of Planck's 3 error estimation methods were biased. The first problem was with the Monte Carlo simulations used to estimate uncertainty. Planck generated thousands of simulated CMB skies to determine how large a dipole you would expect from random fluctuations. But the actual observed sky happened to have a root mean square CMB dispersion, about 12% lower than the average of those simulations. This matters because it means the simulations overestimated the expected noise level, inflating the error bars and making the measured signal look less significant than it actually was. When Atrio-Barandella corrected for this, the statistical significance of Planck's own measured dipole rose from negligible to 98 to 99% confidence. The second problem was with the rotation test. Planck estimated one component of the error by rotating the cluster catalog around the galactic pole and measuring the dipole at each rotation angle. This should have randomized the signal, but because the Milky Way's galactic plane masks a significant fraction of the sky, rotations around the pole do not fully randomize 2 of the 3 dipole components. The result was an artificially inflated uncertainty estimate. In 2015, Atrio-Barandella and Kashlinsky published yet another analysis using both WMAP 9-year and Planck data with 980 clusters. They found dipoles fully compatible with their earlier estimates, independent of frequency, which ruled out thermal SC contamination. The signal was dominated by the most massive clusters and appeared at better than 99% significance when their correction methods were applied. The broader community did not generally accept these rebuttals. The consensus view settled on skepticism that the original Planck analysis was sound, that the corrections were overly aggressive, and that the failure of multiple independent teams to reproduce the signal was more telling than the statistical arguments of the original discoverers. But it is worth noting that Atrio-Barandella's methodological critiques were never definitively refuted in the literature. There was no paper saying, "Here is exactly why the 12% RMS discrepancy does not matter." The debate simply stopped. After 2015, the team published no further papers on dark flow using KSE data. The field moved on, filing dark flow somewhere between probably wrong and not quite dead. And that might have been the end of it. An ambitious measurement that generated a few years of heated argument and then faded into the background. But there is a twist in this story that elevates it from a cautionary tale about noisy data to something far more interesting. Because a theoretical physicist who grew up behind the sealed borders of one of the most isolated countries on Earth had predicted the signal before it existed. And her explanation does not involve any structure within the observable universe at all. Laura Mersini-Houghton was born in 1966 in Tirana, the capital of Albania, at a time when the country was arguably the most isolated nation on Earth. Enver Hoxha's communist dictatorship had broken with the Soviet Union for being too liberal, broken with China for being too revisionist, and sealed Albania's borders so thoroughly that leaving the country without permission was punishable by imprisonment or death. Foreign books were banned. Western music was banned. Religion was banned. The country declared itself the world's first officially atheist state. Intellectual life was suffocated by paranoia and ideological control, and science education was subordinated to Marxist-Leninist orthodoxy in ways that make the Lysenko affair in the Soviet Union look mild by comparison. Mersini-Houghton's family had what the regime called a bad biography, meaning they were classified as politically unreliable, descendants of the pre-communist educated class. In Hoxha's Albania, your biography determined everything: where you could live, what schools you could attend, what jobs you could hold, whether you could travel within the country. A bad biography meant permanent, second-class citizenship, a stain that passed from generation to generation. Mersini-Houghton has spoken publicly about growing up under these conditions, about the suffocating fear that permeated daily life, and about the hunger for intellectual freedom that drove her to excel in the one domain where objective truth still mattered, regardless of ideology: mathematics. Despite these constraints, she rose through the Albanian education system by sheer ability, excelling in mathematics and physics competitions. After the fall of communism in 1991, the borders opened and Mersini-Houghton left Albania. She eventually made her way to the United States, becoming the first Albanian Fulbright scholar in the natural sciences, a distinction that carried enormous symbolic weight for a country that had been sealed off from the international scientific community for half a century. She earned her PhD in physics at the University of Wisconsin at Milwaukee, studying the quantum mechanics of black holes and the early universe. She held positions at several universities before joining the faculty at the University of North Carolina at Chapel Hill, where she has remained as a professor of theoretical physics and cosmology. Her trajectory from Hoxha's Albania to a tenured professorship at a major American research university is remarkable in itself, but it is her theoretical work that matters for our story. She focuses on one of the deepest questions in modern physics: the initial conditions of the universe. Not what happened after the Big Bang, but why the Big Bang had the specific properties it did. Why did inflation start when it did? Why did it produce this particular universe with these particular constants? Why is the cosmological constant, the energy density of empty space, so absurdly small compared to what quantum field theory predicts, yet not exactly zero? These are not small questions. They are the questions that sit at the intersection of quantum mechanics, general relativity, and string theory, the frontier where our best theories break down. In the framework of string theory, there exists a vast landscape of possible vacuum states, perhaps 10 to the 500th or more, each corresponding to a universe with different physical laws, different particle masses, different numbers of spatial dimensions, different strengths of the fundamental forces. Our universe, in this picture, is one bubble nucleated on this landscape. Eternal inflation, a variant of standard inflation in which the inflationary process never fully stops but continually spawns new regions of space, creates new bubble universes in an unending cascade, each with potentially different physics. Most of these bubbles are forever beyond our reach, separated from us by regions of space that are expanding too fast for light or gravity to cross. But forever beyond our reach does not necessarily mean without any influence. In 2006, 2 years before Kashlinsky published his dark flow measurement, Mersini-Houghton and our collaborator Richard Holman of Carnegie Mellon University published a series of papers that derived specific, testable predictions from this landscape framework. Their approach was unusual. Rather than treating our universe as an isolated system, they considered the quantum mechanical interaction between our Hubble volume and the rest of the landscape. In quantum mechanics, systems that were once connected remain entangled, meaning measurements on one system are correlated with the state of the other. Mersini-Houghton and Holman argued that our universe retains a quantum entanglement with neighboring bubble universes on the string landscape, and that this entanglement has observable consequences. The mathematics of their framework, which they called the quantum mechanical formulation of the landscape multiverse, led to several predictions. First, the entanglement would produce an effective repulsive force on our universe from neighboring bubbles, which would manifest as a giant void in the CMB, a region with anomalously low temperature. Second, the same interaction would produce an alignment of the lowest multipoles of the CMB power spectrum, what would later become known as the axis of evil. And third, the gravitational influence of the nearest and most massive neighboring bubble universe would induce a coherent bulk flow across the observable universe, a tilt in the gravitational potential that would cause matter to stream in one direction. They calculated this velocity to be approximately 670 kilometers per second. Think about that timeline. In 2006, Mersini-Houghton published a prediction derived from quantum cosmology on the string landscape that the universe should exhibit a bulk flow of about 670 kilometers per second. 2 years later, in 2008, Kashlinsky measured a bulk flow of 600 to 1,000 kilometers per second. The agreement was striking, not exact, but the predicted value fell squarely within the measured range, and it was derived not from fitting parameters to the data, but from fundamental physics. This is a crucial distinction in science. Many theories are flexible enough to accommodate observations after the fact, adjusting their parameters to match whatever the data show. This is called post-diction. And while it is not worthless, it carries far less weight than genuine prediction. Mersini-Houghton's number was a prediction. It was calculated before the measurement existed, published in peer-reviewed journals, and left no room for parameter adjustment. When Kashlinsky's value came in, the agreement was either an extraordinary coincidence or evidence that the landscape framework captures something real about the universe. The predicted direction, broadly toward the same region of sky, was also consistent, and the CMB cold spot, a 5-degree wide region of anomalously low temperature that had been discovered in 2004 by Lawrence Rudnick and colleagues using WMAP data, fit perfectly as the void predicted by the landscape entanglement. The cold spot is one of the most puzzling features in the CMB. It is about 70 microkelvins colder than the average CMB temperature in a region about 10 degrees across, centered at galactic coordinates roughly L equals 209 degrees, B equals -57 degrees. Its probability of occurring by chance in a standard lambda CDM universe is less than 1 in 500. Mersini-Houghton's framework predicted exactly such a feature, arising from the repulsive entanglement interaction with a neighboring bubble. Mersini-Houghton immediately recognized the connection and began making the case publicly. She gave a TEDx talk and several high-profile lectures arguing that dark flow, the cold spot, and the axis of evil together constituted the first observational evidence for the multiverse. The narrative was electrifying. A woman who had grown up in one of the most intellectually repressive societies on Earth had developed a theory predicting that our universe is just one bubble in an infinite sea, and 3 separate observations seemed to confirm it. It was the kind of story that science journalism thrives on, and it received widespread coverage. But the scientific community's response was complicated. and for reasons that go deeper than the usual skepticism toward bold claims. The first issue was specificity. While the predicted velocity of 670 kilometers per second was impressively close to the measured range, the prediction depended on assumptions about the string landscape that are themselves untested. The landscape is a theoretical construct derived from string theory, and string theory itself has not been experimentally verified. Deriving a number from a framework that lacks independent confirmation, and then claiming that the agreement of that number with an observation confirms the framework, is a form of circular reasoning that many physicists found uncomfortable. The second issue was falsifiability. When the Planck satellite failed to confirm dark flow and set an upper limit well below the claimed signal, Mersini-Houghton did not retract her prediction. She argued that the CMB cold spot and the multipole alignments still supported the landscape theory, and that dark flow might be detectable at different scales or with different methods. Critics pointed out that if a theory's predictions are confirmed, the theory is supported, but if the predictions fail, the theory is also supported through reinterpretation, then the theory is not really being tested at all. Karl Popper, the philosopher of science who formalized the concept of falsifiability, would have had concerns. This is not to say Mersini-Houghton's work is unserious. It is mathematically rigorous, published in respected journals, and addresses a genuine gap in our understanding. The question of initial conditions is real, and the landscape is a legitimate theoretical framework, even if it is unverified. The problem is that the observational consequences she predicts are individually ambiguous. The CMB cold spot might be a void along the line of sight, a statistical fluctuation, or evidence of a neighboring universe, and current data cannot distinguish these possibilities. The axis of evil might be a real cosmological signal, an artifact of foreground subtraction, or the result of our local motion, and dark flow might be real, might be a systematic error, or might emerge from independent observations at a different amplitude than predicted. Christos Tagas, a theoretical cosmologist at Aristotle University of Thessaloniki in Greece, proposed in 2012 that a dark flow-like bulk motion could produce effects that mimic dark energy, the mysterious force driving the accelerating expansion of the universe. His argument was built on an observation that relativists had known about but rarely applied to real cosmological data. An observer embedded in a large-scale bulk flow does not inhabit a perfectly isotropic universe, and the deviations from isotropy produce measurable effects on how that observer interprets cosmological data. Specifically, the peculiar velocity of the observer introduces anisotropic terms into the deceleration parameter, the quantity that measures whether the expansion of the universe is speeding up or slowing down. In Sargas's framework, an observer riding the bulk flow would measure a smaller deceleration, or equivalently, a larger apparent acceleration in the direction of the flow compared to the perpendicular directions. If the flow were large enough, the net effect, averaged over the sky, could mimic a cosmological constant. This was a remarkable suggestion because it offered a potential connection between two of the deepest mysteries in cosmology, the unknown cause of cosmic acceleration and the unknown cause of large-scale bulk flows. Dark energy, the dominant component of the universe's energy budget, comprising about 68% of the total, has resisted identification for over 2 decades since its discovery in 1998 by 2 independent supernova teams led by Saul Perlmutter and by Brian Schmidt and Adam Rees. Its simplest form, the cosmological constant, requires a value so precisely tuned that explaining it from fundamental physics has been called the worst prediction in the history of science. The discrepancy between the quantum field theory prediction and the observed value spanning 120 orders of magnitude. Every atom, every photon, every galaxy in the universe is immersed in this sea of dark energy. Yet no laboratory experiment has ever directly detected it. If Sargas was right, dark energy might not be a property of space itself, but a consequence of our motion through it, a kinematic illusion created by our failure to account for the non-isotropic conditions in which we observe the universe. The idea was not that dark energy does not exist, but that its apparent magnitude might be enhanced or even partially explained by the same bulk flow that Kashlinsky had measured. But this idea too remained speculative because it depended on dark flow being real and having the right magnitude and direction. And by 2013, the observational case for dark flow was in ruins. Subsequent calculations also showed that the effect, while real in principle, would require bulk flows at the extreme end of what Kashlinsky claimed to produce a significant fraction of the observed acceleration. The multiverse prediction was tantalizing but unfalsifiable. The dark energy connection was elegant but contingent, and the only direct measurement had been contradicted by a better instrument. So by the mid-2010s, dark flow occupied a peculiar position in cosmology, not definitively dead, because the technical rebuttal to Planck had never been answered, not alive, because no independent team had confirmed it, not meaningful, because the theoretical interpretations were either untestable or dependent on the signal being real. It was a ghost in the data, occasionally invoked in review papers and popular science articles, but not the subject of active research. And then the universe itself started producing evidence that something was genuinely wrong, with the assumption that space has no preferred direction. The first signs had been there all along, hiding in plain sight in the CMB. The Planck satellite, the same instrument that had challenged dark flow, confirmed a series of anomalies in the CMB that were individually mild but collectively troubling. These anomalies had been first glimpsed in WMAP data, but were widely expected to disappear when Planck provided its vastly superior measurements. They did not disappear. They persisted, and in some cases, grew more statistically significant. The hemispherical power asymmetry is perhaps the most striking. When you divide the CMB sky into two hemispheres, one centered on a specific direction in the constellation Pegasus, and the other on the opposite side, the fluctuations in one hemisphere are systematically larger than in the other by about 7%. This should not happen. In a statistically isotropic universe, the fluctuations should be the same, on average, in all directions. The asymmetry exceeded 3 sigma in the Planck data, and attempts to explain it through foreground contamination, systematic errors, or known selection effects have failed. It appears to be a real feature of the primordial universe. The quadrupole-octopole alignment, which Kate Land and João Magejo at Imperial College London christened the axis of evil in 2005, is another anomaly that refuses to go away. The quadrupole and octopole are the largest scale patterns in the CMB fluctuations, corresponding to angular scales of 90 and 60 degrees respectively. In a statistically isotropic universe, the orientations of these patterns should be random, like the spin axes of tops scattered across a floor. Instead, they are aligned with each other and with the ecliptic plane, the plane of Earth's orbit around the Sun, at 2 to 3 sigma significance. The alignment with the ecliptic is particularly disturbing because it suggests either a systematic error related to our solar system's geometry or a genuine cosmological effect that happens by bizarre coincidence to align with our local astronomical reference frame. And the CMB cold spot remained stubbornly anomalous, 5 degrees across, about 70 microkelvins colder than average, with an unusual internal structure showing a cold core surrounded by a hot ring. To appreciate how strange this is, consider that the typical temperature fluctuations in the CMB are about 18 microkelvins, meaning the cold spot represents a deficit roughly 4 times the typical fluctuation amplitude, sustained over an enormous angular area. Its probability of occurring by chance in a standard lambda CDM universe has been estimated at less than 0.2% by multiple independent analyses, making it one of the least likely features in the entire CMB sky. A 2015 study by Istvan Sapudi and colleagues proposed that the cold spot was caused by a supervoid, an enormous region of underdense space about 3 billion light-years away along the line of sight. The Eridanus supervoid is real and was confirmed by galaxy surveys, but subsequent analyses showed that it was not large enough or empty enough to fully account for the cold spot's temperature deficit through the integrated Sachs-Wolf effect, the mechanism by which photons lose energy as they traverse an expanding void and do not fully regain it when they exit, because the void has continued to expand during the transit. The cold spot remains partially unexplained, a stubborn outlier that fits comfortably into Mersini-Houghton's multiverse framework, but refuses to be explained by anything within the standard model. None of these anomalies, taken individually, constituted a crisis. 2 to 3 sigma signals appear and disappear in cosmological data all the time, and with enough statistical tests on a rich data set like the CMB, some apparent anomalies are expected by chance alone. This is the look elsewhere effect, the statistical inflation that occurs when you test many hypotheses on the same data. If you flip a coin 1,000 times, some sequence of 50 flips somewhere in that run will look improbable. That does not mean the coin is biased. Cosmologists have debated for years whether the CMB anomalies are genuine features of the primordial universe, or statistical flukes amplified by human pattern recognition and the very human desire to find something interesting in the data. But they all pointed in roughly the same direction, toward a breakdown of statistical isotropy at the largest scales, the hemispherical asymmetry, the quadrupole-octopole alignment, and the cold spot all involve the largest angular scales in the CMB, the scales most sensitive to the overall geometry and boundary conditions of the observable universe. If the universe has a preferred direction, a large-scale tilt or gradient left over from conditions before or during inflation, it would show up most prominently at exactly these scales, and the directions of the anomalies, while not perfectly aligned with each other or with the dark flow direction, cluster in the same general region of the sky, a pattern that is suggestive even if not yet conclusive. In 2023, a team led by Richard Watkins, Hume Feldman, and Michael Hudson published the most precise measurement of large-scale bulk flows ever conducted using the Cosmic Flows 4 database. This was a completely different approach from Kashlinsky's, Instead of using the KSSE effect on the CMB, they used direct distance measurements to galaxies, compiled from multiple techniques including the Tully-Fisher relation, which correlates a spiral galaxy's rotational velocity with its intrinsic luminosity, the fundamental plane, which does something similar for elliptical galaxies using their size, surface brightness, and velocity dispersion. And Type Ia supernovae, the standardizable candles that won the 2011 Nobel Prize for their role in discovering the accelerating expansion of the universe. The Cosmic Flows 4 catalog contained over 56,000 galaxy distances, the largest such compilation in history, assembled over years of painstaking observational work by Brent Tully at the University of Hawaii and an international network of collaborators. The method is conceptually straightforward, even if technically demanding. If you know a galaxy's true distance and its observed redshift, you can calculate what its recession velocity should be from the Hubble expansion alone. Any difference between the predicted velocity and the observed velocity is the galaxy's peculiar velocity, its motion through space due to gravitational attraction from surrounding matter. Compile enough of these measurements across a large enough volume, and you can map the bulk flow, the average coherent motion of galaxies on different scales. And their result was alarming. At scales of 200 megaparsecs per h, roughly 650 million light-years, they measured a bulk flow that was in 4.8 sigma tension with the predictions of lambda CDM. The standard model predicts essentially negligible bulk flows at those scales, a few tens of kilometers per second at most. The measured flow exceeded 400 kilometers per second. This was not a reanalysis of WMAP or Planck data. It was an entirely independent measurement using completely different observables, different instruments, and different systematic errors. The cluster catalog came from galaxy surveys, not X-ray observations. The velocity measurement came from distance indicators, not CMB temperature shifts. And the direction of the flow was broadly consistent with the dark flow direction Kashlinsky had reported 15 years earlier. The significance of cosmic flows 4 extends beyond its headline number. What makes this result so difficult to dismiss is the sheer diversity of the distance indicators that feed into it. The Tully-Fisher relation, which correlates a spiral galaxy's rotation speed with its intrinsic brightness, has been calibrated and tested over 4 decades. The fundamental plane for elliptical galaxies, discovered independently by Sandra Faber's group and by Roger Davies and colleagues in the late 1980s, relies on 3 separate observables and has its own independent calibration history. Type Ia supernovae provide the most precise individual distance measurements, accurate to about 5 to 7% per object, and they are the same standardizable candles that won the Nobel Prize for discovering cosmic acceleration. Each of these techniques has its own systematic errors, its own calibration uncertainties, its own potential biases, but those systematics are different for each method. Tully-Fisher is sensitive to galaxy inclination and internal extinction. The fundamental plane depends on stellar population models. Supernovae depend on light curve fitting and reddening corrections. For all 3 methods to conspire to produce the same spurious bulk flow in the same direction would require an extraordinary coincidence of independent systematic errors, and no one has identified a plausible mechanism for such a conspiracy. Let that sink in. A 4.8 sigma tension is enormous by cosmological standards. In particle physics, 5 sigma is the gold standard for claiming a discovery. The Higgs boson was announced at 5 sigma. Gravitational waves were confirmed at 5.1 sigma. Cosmic flows. Fall was knocking on that door with a measurement that contradicted one of the core predictions of the standard cosmological model, that the universe should be statistically homogeneous and isotropic on the largest scales. And unlike Kashlinsky's measurement, which relied on a single subtle effect extracted from a single dataset, this result was built on tens of thousands of independent galaxy distance measurements accumulated over decades, and the evidence kept accumulating. In 2021, Nathan Sechrest, Sebastian von Halsegger, and Mohamed Ramiz published a study of over 1.3 million quasars observed by the Wide Field Infrared Survey Explorer, or WISE, measuring the cosmic radio dipole. To understand why this matters, you need to know about one of the most basic predictions of standard cosmology. Every introductory cosmology textbook explains that the CMB has a dipole, a direction in which the sky is slightly hotter, and an opposite direction where it is slightly cooler. And this dipole is interpreted as the Doppler effect of our motion through space at about 370 kilometers per second toward the constellation Leo. This is our peculiar velocity relative to the CMB rest frame, the frame in which the radiation from the Big Bang looks the same in all directions. It is a well-measured, well-understood number, and it forms the basis for how we define at rest in cosmology. Here is the key prediction. If our motion through space at 370 kilometers per second fully explains the CMB dipole, then the distribution of distant quasars, and indeed any population of distant cosmological sources, should show a corresponding dipole of the same direction and a specific predictable amplitude. This is because our motion does not just Doppler shift the CMB, it also aberrates and boosts the apparent distribution of distant objects, making them appear slightly denser in the direction we are moving toward, and slightly sparser in the direction we are moving away from. The effect is a consequence of special relativity applied to source counts, first worked out in detail by George Ellis and John Baldwin in the 1980s, and it is one of the cleanest predictions in all of cosmology. The predicted amplitude of this effect is determined entirely by our velocity and the spectral properties of the source population. There is no free parameter. There is no wiggle room. It is a sharp, testable prediction that any survey of sufficiently distant objects should confirm if the standard framework is correct. The quasar dipole does not match. It is 2 to 4 times larger than the kinematic prediction. The direction is roughly consistent with the CMB dipole, but the amplitude is wildly off. The significance of this discrepancy has grown with each subsequent analysis, as the catalogues have expanded and the systematic errors have been better characterized. By 2025, the most recent assessments published in Reviews of Modern Physics placed the discrepancy at over 5 sigma, making it one of the most statistically significant anomalies in all of observational cosmology. If our motion through space fully explains the CMB dipole, the quasar dipole should match it. It does not. This means either the CMB dipole is not entirely kinematic, meaning the universe itself has an intrinsic dipole, some residual anisotropy baked into the fabric of space, or our motion through space is not 370 kilometers per second, as inferred from the CMB, or there is some other systematic effect that no one has identified. Each of these possibilities is radical. An intrinsic CMB dipole would violate the cosmological principle directly. A different velocity would mean our entire framework for interpreting the CMB is wrong, and the unknown systematic explanation is the refuge of the desperate, acceptable as a hypothesis but not as a conclusion, because 5 sigma demands an explanation. This is called the cosmic dipole tension, and it is arguably the most underreported anomaly in modern cosmology. It has received a fraction of the attention lavished on the Hubble tension, despite being at comparable or higher statistical significance. The reasons for this relative obscurity are sociological as much as scientific. The Hubble tension involves a direct clash between 2 well-understood, high-profile measurements, both of which have armies of researchers behind them, Nobel Prize winners on their teams, and billions of dollars of telescope time invested. It produces a clean, quotable number. The expansion rate is either 73 or 67, and somebody must be wrong. The cosmic dipole tension, by contrast, involves an abstract prediction from special relativity applied to source counts, a measurement that most astronomers find conceptually unfamiliar, and an implication so radical that many would prefer not to think about it. If the CMB dipole is not entirely kinematic, then one of the most basic assumptions in all of cosmology, that the CMB defines a universal rest frame and our motion through it fully explains the dipole, is wrong. The downstream consequences cascade through every cosmological measurement that uses the CMB rest frame as a reference, and its existence lends retrospective credibility to the idea that the universe genuinely has a preferred direction, which is exactly what Darkflow claimed. In 2024, a team analyzing galaxy cluster motions within the framework of F of R modified gravity theories, which extend general relativity by adding curvature-dependent terms to Einstein's field equations, reported a bulk flow of 998 plus or minus 102 kilometers per second for clusters at redshifts between 0.1 and 0.2. The F of R framework modifies how gravity behaves at the very largest scales, allowing for stronger gravitational interactions over cosmological distances than general relativity permits. In these models, the same galaxy clusters that Kashlinsky and Planck studied would be more strongly pulled by distant mass concentrations, potentially producing the bulk flows that standard gravity cannot explain. The amplitude they found is remarkably close to Kashlinsky's original claim. The analysis used a different theoretical framework, different data, and a completely different methodology, but arrived at a number that would have been familiar to anyone who read the 2008 paper. And the direction, once again, pointed toward the same general region of sky. Here is the pattern that emerges when you step back and look at the full picture. In 2008, Kashlinsky found a bulk flow of 600 to 1,000 kilometers per second using the KSSE effect. In 2006, Mersini-Houghton predicted 670 kilometers per second from Multiverse physics. In 2013, Planck set an upper limit of 254 kilometers per second using KSZ, apparently killing the claim. But in 2003, cosmic flows, 4 found bulk flows at 4.8 sigma tension with lambda CDM, using galaxy distances. In 2025, the cosmic radio dipole anomaly exceeded 5 sigma using quasar catalogs, and in 2024, modified gravity analysis found 998 kilometers per second using cluster dynamics. The original KSZ detection remains unconfirmed by independent teams using the same method. But the broader claim that the universe exhibits large-scale bulk flows inconsistent with standard cosmology is now supported by multiple independent lines of evidence at significance levels that would be considered discoveries in other fields of physics. Dark flow, the specific measurement, may have been wrong or at least overstated, but the phenomenon it pointed to, a universe with a preferred direction of motion at scales where no preferred direction should exist, appears increasingly real. This is the pattern that makes the dark flow story so compelling and so unusual in the history of cosmology. Most controversial measurements either get confirmed and enter the canon, or get refuted and disappear. Dark flow did neither. The specific measurement faded into disputed territory, but the broader question it raised, whether the universe is truly isotropic at the largest scales, has come roaring back with evidence from completely unrelated observations. It is as if a prospector drilled for oil in a particular spot, hit something ambiguous, was told by every geologist that there was nothing there, and then watched as 3 other companies drilling at different spots with different equipment all struck the same underground reservoir. The original borehole may have been flawed, but the oil is real. There is even a connection to the biggest unsolved problem in observational cosmology, and it is a connection that might eventually unify several seemingly separate anomalies into a single picture. The Hubble tension is the persistent disagreement between the expansion rate of the universe, measured locally using supernovae and Cepheid variables, roughly 73 kilometers per second per megaparsec, as determined by Adam Rees and the SH0ES team, and the rate inferred from the CMB using the standard lambda CDM model, roughly 67.4, as determined by the Planck collaboration. The discrepancy is now at about 5 sigma and has resisted every attempt at explanation for over a decade. In 2024, multiple papers explored the possibility that a large-scale bulk flow could systematically bias local measurements of the Hubble constant, producing an apparent acceleration that is not real, but rather a kinematic effect of our motion through a universe that is not as homogeneous as we assumed. The logic is subtle but compelling. If we are embedded in a bulk flow, then the supernovae we observe in the direction of that flow will appear to recede faster than the Hubble expansion alone would predict, and supernovae in the opposite direction will appear to recede slower. If the bulk flow is large enough and extends far enough, the net effect on a locally measured Hubble constant could be a systematic upward bias of several kilometers per second per megaparsec, exactly the right magnitude and direction to explain the tension. The SH0ES team measures the Hubble constant using supernovae within a few hundred megaparsecs. If that volume is embedded in a bulk flow toward the dark flow direction, the local expansion rate would appear systematically faster than the global rate inferred from the CMB. The disagreement would be real but not fundamental. It would be a measurement of our local motion disguised as a measurement of cosmic expansion. If true, dark flow and the Hubble tension are not separate problems. They are the same problem, seen from different angles, and solving one might solve the other. The standard cosmological model, lambda CDM, is not broken in the catastrophic sense. It remains one of the most successful theories in all of science, capable of fitting the observed CMB power spectrum with 6 parameters to a precision that would make most other fields of science envious. It correctly describes the large-scale distribution of galaxies, the abundance of light elements from Big Bang nucleosynthesis, the growth of structure over cosmic time as measured by galaxy surveys and weak gravitational lensing, and the distance redshift relationship traced by Type Ia supernovae. It predicted the existence of baryon acoustic oscillations in the galaxy distribution before they were observed, and it predicted the detailed pattern of CMB polarization that Planck subsequently confirmed. By almost any measure, lambda CDM is a triumph. But at the largest scales, at the boundary where the homogeneous approximation is supposed to hold, the model is accumulating tensions that collectively tell a story of incompleteness. The Hubble tension, now at roughly 5 sigma, and resistant to every systematic explanation that has been proposed, from photometric calibration errors to Cepheid crowding to local void effects. The S8 tension, a persistent 2 to 3 sigma disagreement between the clumpiness of the universe as inferred from the CMB and as measured by weak gravitational lensing surveys like the Dark Energy Survey and the Kilodegree Survey, suggesting that matter is less clustered on small scales than lambda CDM predicts, as if gravity is slightly weaker than expected at pulling matter together since the epoch of recombination. The cosmic dipole anomaly at over 5 sigma, the CMB anomalies at 2 to 3 sigma each, persistent across 2 independent satellite missions. The cosmic flows, 4 bulk flow excess at 4.8 sigma. The lensing anomaly in Planck data, where the CMB appears slightly more gravitationally lensed than the best fit lambda CDM model predicts, at about 2 to 3 sigma. None of these individually falsify the model. Each can be argued away as a statistical fluctuation, a systematic error, or a feature that falls within the broad range of outcomes consistent with lambda CDM if you squint hard enough. But taken together, they form a pattern that is becoming increasingly difficult to dismiss as coincidence. They suggest that the universe at the largest scales is not as simple, not as isotropic, not as homogeneous as lambda CDM assumes, and the direction in which many of these anomalies point, both literally in terms of sky direction and figuratively in terms of the kind of new physics they imply, is exactly the world dark flow pointed toward in 2008. So where does this leave us? The original measurement is disputed. The theoretical explanation is unfalsifiable with current data. But the broader phenomenon, a universe with anomalous large-scale motions and a possible preferred direction, is now supported by independent evidence at levels that demand explanation. What is needed is not another reanalysis of old data, not another theoretical framework, but a definitive new measurement that can settle the question one way or the other. And Alexander Kashlinsky has designed exactly that. After the dark flow controversy subsided, Kashlinsky did not retreat into other research topics or accept the consensus that his measurement was wrong. He did something that reveals either extraordinary stubbornness or extraordinary confidence, depending on your perspective. He pivoted. Rather than continuing to fight over KSS stacking techniques and Planck error bars, arguments that had become increasingly technical and increasingly circular, he conceived an entirely different way to test the same underlying question. Is the universe at rest, or is it moving? The key insight was to look for the same signal in a completely different background. The KSSD method uses the CMB as a backlight and galaxy clusters as moving mirrors. The limitation of this approach, as the Planck controversy demonstrated, is that the KSZ signal is tiny, buried under multiple layers of foreground contamination, and dependent on assumptions about cluster physics that are difficult to verify independently. What Kashlinsky needed was a different cosmic background, one that could serve as an independent reference frame for measuring the motion of the universe. The idea centers on the cosmic infrared background, the CIB, just as the CMB is the afterglow of the Big Bang, released 380,000 years after the beginning of time. The CIB is the accumulated infrared light from all the stars and galaxies that have ever existed, stretching back to the first generation of stars in the universe. Every star that has ever burned, every galaxy that has ever shone, has contributed photons to this diffuse infrared glow that pervades the sky. The CIB peaks at wavelengths around 1 to 200 micrometers, but extends across a broad range of infrared wavelengths, and it contains information about the entire history of star formation and galaxy evolution. Here is the critical point. If we are moving through space at 370 kilometers per second, as the CMB dipole suggests, then the CIB should also have a dipole, because our motion Doppler shifts and aberrates the infrared background just as it does the microwave background. The CIB dipole should point in the same direction as the CMB dipole and have a specific amplitude that can be calculated from our velocity and the spectral properties of the CIB. If you measure the CIB dipole and it matches the prediction, the universe is consistent and the CMB dipole is indeed purely kinematic. If the CIB dipole does not match, something is fundamentally wrong. Either our velocity is different from what the CMB implies, or the CMB has an intrinsic dipole component that is not due to our motion, or the universe itself has a large-scale anisotropy that manifests differently in different backgrounds. This is the principle behind near-BAID, the near-infrared background dipole experiment. Kashlinsky proposed it as part of the European Space Agency's Euclid mission, a space telescope launched in July 2023 from Cape Canaveral aboard a SpaceX Falcon 9 rocket. Euclid's primary mission is to study dark energy and dark matter through gravitational lensing and galaxy clustering, mapping the three-dimensional distribution of billions of galaxies across a third of the sky. But its wide-field, near-infrared imaging capabilities provided by the NASP instrument operating at wavelengths between 0.9 and 2.0 micrometers make it uniquely suited for measuring the CIB with the sensitivity and sky coverage needed to detect its dipole. The challenges are formidable. The CIB at near-infrared wavelengths is contaminated by zodiacal light, the sunlight scattered by interplanetary dust in our own solar system, which is orders of magnitude brighter than the CIB itself. There is also scattered light from stars in the Milky Way, thermal emission from the telescope and instruments, and various instrumental systematics that must be modeled and removed. Previous attempts to measure the CIB dipole from ground-based or earlier space-based observations were limited by these foregrounds and by insufficient sky coverage. Euclid changes the equation because its survey will eventually cover about 15,000 square degrees of sky with uniform near-infrared photometry, providing the statistical leverage needed to separate the CIB dipole from the foreground contamination. In 2024, the Euclid collaboration published a detailed methodology paper with Kashlinsky as a lead author, laying out how NIRBADE will work. The paper described the expected sensitivity, the foreground subtraction strategy, the systematic error budget, and the criteria for a detection. It was a blueprint for an experiment that could settle a 17-year-old controversy. The methodology was reviewed and accepted by the Euclid collaboration's internal review process, which means it carries the weight of one of the largest scientific collaborations in Europe. Fernando Atrio Barandella is a co-author on the NIRBADE papers. He is also a member of both the Planck collaboration and the Euclid collaboration, one of the very few scientists who straddles both the instrument that challenged dark flow and the instrument that might confirm it. His presence on the NIRBADE team is a quiet testament to the fact that the dark flow question was never truly resolved, only deferred. The same man whose error analysis was dismissed by the Planck majority is now designing the next generation of the test, using better data and a completely independent observable. The irony of Kashlinsky's career arc is difficult to miss. The boy from Soviet Riga who read Stanislaw Lem's The Magellanic Cloud and decided to understand the largest structures in the universe has spent more than 3 decades at NASA studying the cosmic, infrared background, and bulk motions. His early work focused on the CIB itself, measuring its properties and fluctuations, and what they reveal about the first stars and the epoch of reionization, the period when ultraviolet radiation from the first luminous objects reionized the neutral hydrogen that had filled the universe since recombination. That expertise, accumulated over years of painstaking work on a topic that few other cosmologists found glamorous, became the foundation for NIRBADE. He proposed the most controversial measurement in observational cosmology, weathered years of criticism and contradiction, watched the community largely dismiss his result, and then designed a new experiment on a European Space Telescope to test the very question the controversy raised, using the cosmic background he had spent his career studying. Whether you view this as vindication or as a man unable to let go of a flawed result depends on whether NIRBADE confirms or denies the dark flow hypothesis. The data will decide. But there is something deeply admirable about a scientist who, when told his measurement was wrong, does not simply argue louder about the old measurement, but instead invents a completely new way to ask the same question. That is the scientific method at its most stubborn and most honest. The timeline for results is uncertain but finite. Euclid's survey is ongoing, with early data releases expected in the coming years, and the systematic challenges of measuring the CIB dipole are formidable. But the methodology is sound, the team is experienced, and the data will be orders of magnitude better than anything previously available. Meanwhile, other experiments are converging on the same questions from different directions, creating a web of complementary probes that will be difficult for any single anomaly to escape. The Simons Observatory, a ground-based CMB experiment in the Atacama Desert of Chile, at an altitude of 5,200 meters, named after the late philanthropist and mathematician James Simons, began observations in 2024. The Atacama is one of the driest places on Earth, and its extreme altitude puts the telescopes above most of the atmospheric water vapor that absorbs microwave radiation, making it one of the best sites on the planet for CMB observations. Rivaled only by the South Pole, the observatory combines large and small aperture telescopes with over 60,000 superconducting detectors cooled to fractions of a degree above absolute zero, achieving far better sensitivity than either WMAP or Planck, particularly for the small-scale temperature fluctuations that carry the KSZ signal. If dark flow exists at any amplitude above about 200 kilometers per second, the Simons Observatory should detect it within a few years of operation, using the same KSZ stacking technique Kashlinsky pioneered, but with data that is dramatically cleaner and more sensitive. The Vera C. Rubin Observatory, named after the pioneering astronomer who provided some of the first compelling evidence for dark matter through her studies of galaxy rotation curves in the 1970s, is perched on Cerro Pachon in Chile. It will begin the legacy survey of space and time in the mid-2020s, imaging the entire southern sky every few nights for a decade using the largest digital camera ever constructed, a 3.2 billion pixel detector the size of a small car. When complete, the LSST will have measured the positions, brightnesses, and photometric redshifts of roughly 20 billion galaxies and the distances and light curves of hundreds of thousands of Type As supernovae. This will provide an independent bulk flow measurement with statistical power that dwarfs cosmic flows, extending to much greater depths and covering a far larger volume. If the 4.8 sigma tension persists at LSST's precision, it will be very difficult to attribute to systematic errors. And the Square Kilometre Array, an international radio telescope project with stations spanning Australia and South Africa, will eventually measure the cosmic radio dipole with enough precision and source count to determine once and for all whether the quasar-dipole anomaly is real or a product of selection effects and calibration errors. The SKA will observe billions of radio sources across the sky, providing a dipole measurement with uncertainties small enough to distinguish between a purely kinematic origin and an intrinsic cosmological anisotropy. There was a setback. CMB S4, the next-generation ground-based CMB experiment that would have deployed over 500,000 detectors across multiple sites in Chile and Antarctica, providing the most definitive KSZ measurements ever made, was cancelled by the United States National Science Foundation in July 2025 due to budget constraints. CMB S4 would have measured the KSZ effect for tens of thousands of galaxy clusters compared to the hundreds used by Kashlinsky and the thousands used by Planck, and it would have been sensitive enough to detect a bulk flow as small as 50 kilometers per second. Its cancellation means that the most precise bulk flow measurement using the KSZ-HEM method will not happen on the originally planned timeline, a loss that the cosmological community is still reckoning with. But the question will still be answered, because the evidence is no longer confined to one method or one dataset. It is emerging from galaxy surveys, quasar catalogs, infrared backgrounds, and CMB measurements independently. The universe appears to be telling us the same thing through multiple messengers, and even without CMB S4, the convergence of the remaining experiments may be enough. If dark flow is real, or more precisely, if the universe genuinely has anomalous large-scale bulk motions and a preferred direction inconsistent with standard inflation, the implications cascade outward from cosmology into the deepest questions in physics. The most conservative possibility is that inflation happened, but was shorter or more complex than the simplest models assume. If inflation lasted just barely long enough to solve the horizon and flatness problems, but not long enough to completely erase pre-inflationary structure, then residual gradients in the gravitational potential could persist on the largest observable scales. The universe would still be inflationary, but just barely, with the pre-inflationary initial conditions poking through at the edges like the wrinkles in a balloon that has been inflated almost but not quite enough to smooth them out. This scenario is testable because it predicts specific correlations between the CMB anomalies and the bulk flow direction, correlations that next-generation experiments could confirm or rule out. The more radical possibility is the one Mersini-Houghton articulated. Our observable universe is one bubble in a larger multiverse, and the dark flow is the gravitational influence of a neighboring bubble universe pulling on everything within ours. We would never be able to observe this other universe directly because it lies beyond the cosmic horizon and is receding from us faster than light. No signal, no photon, no gravitational wave could ever cross the gap, but its gravitational influence, imprinted during the earliest moments of our universe's existence, when the two bubbles were close enough to interact quantum mechanically, would be felt as a tilt, a gentle, persistent pull on every galaxy cluster in the observable universe, like a current in an ocean whose shore you can never reach. If this is correct, then the universe as we know it, everything within the cosmic horizon, all 100 billion galaxies, all 100 trillion stars, the entire cosmic web spanning 93 billion light-years, is embedded in something incomprehensibly larger, and that larger structure has left its fingerprint on the motion of everything within our reach. And the most radical possibility of all is that the cosmological principle itself is wrong, not approximately wrong, not slightly violated, but fundamentally mistaken. The universe at the largest scales might not be homogeneous or isotropic. It might have structure, gradients, and preferred directions all the way up, with no scale at which it smooths out into the featureless uniformity that lambda CDM assumes. This would not invalidate general relativity or the Big Bang, but it would require a complete rethinking of the boundary conditions of the universe, a new answer to the question of why space looks the way it does. The mathematics of an anisotropic cosmology are far more complex than the isotropic models we currently use, because they break the symmetries that make the equations tractable. But several groups are already developing these frameworks, motivated by the accumulating observational evidence that isotropy may be an approximation rather than an exact truth. The Bianchi models, a family of solutions to Einstein's equations that allow for anisotropic expansion, have been studied since the 1960s, but have received renewed attention in recent years as potential descriptions of a universe with a preferred direction. They are mathematically demanding and observationally constrained, but they are no longer merely academic exercises. Here is what we know for certain. As of 2025, in 2008, a team at NASA found that hundreds of galaxy clusters were streaming in one direction at a speed that the standard model could not explain. The measurement was controversial, challenged by a graduate student's reanalysis, and then by the most precise CMB satellite ever built, and never independently confirmed using the same method. The man who found it and the man who defended its statistics published a detailed technical rebuttal that the community chose not to engage with, and the debate ended in silence rather than resolution. But the woman who predicted the signal before it was found derived it from the physics of the multiverse, and her predicted velocity of 670 kilometers per second fell squarely within the measured range. And in the years since, independent observations using completely different techniques, different instruments, and different systematic errors have found that the universe does, in fact, exhibit anomalous bulk motions and a possible preferred direction at statistical significance levels that approach or exceed the threshold for discovery in particle physics. The cosmic flows, 4 bulk flow at 4.8 sigma, the cosmic radio dipole at over 5 sigma, the CMB anomalies that persistently refuse to vanish, the Hubble tension that might share a common origin with large-scale flows. Each of these could individually be explained away. Together, they form a pattern that is increasingly difficult to ignore. The original dark flow measurement might have been wrong. The amplitude might have been inflated by systematic errors. The KSS technique might not have been up to the task. But the question Alexander Kashlinsky asked in 2008, whether the observable universe is a complete and self-contained system, or whether it is embedded in something larger that we can never directly see, is now being answered by the universe itself through multiple independent channels, all pointing in the same unsettling direction. We do not yet know what is out there. We do not know if it is another universe, a remnant of pre-inflationary structure, a modification of gravity at the largest scales, or something our current theories cannot describe. But for the first time in the history of cosmology, we have the instruments, the data, and the mathematical frameworks to find out. Euclid is in orbit, collecting near-infrared photons that Kashlinsky will use to measure the CIB dipole. The Simons Observatory is scanning the Atacama sky for the faintest KSC signals. The Vera Rubin Observatory is being commissioned to survey billions of galaxies, and theorists from Chapel Hill to Thessaloniki to Salamanca are developing the frameworks needed to interpret whatever the data reveals. The boy from Riga who read science fiction about voyages to other star systems grew up to detect something that might be the gravitational fingerprint of a neighboring universe. The woman from Tirana who escaped a dictatorship predicted it from the mathematics of the string landscape before anyone had seen it. The Spaniard from the Canary Islands who moved to Salamanca spent a decade defending error bars that the rest of the world dismissed, and the satellite that was supposed to kill the idea instead revealed a universe full of anomalies that nobody can fully explain. Something is pulling on everything we can see. The direction is known, the velocity is debated, the source is invisible. And after 17 years of controversy, stalemate, and the slow accumulation of evidence from instruments scattered across continents and in orbit around the Sun, we are closer than we have ever been to understanding whether the observable universe ends at the cosmic horizon, or whether it is just a small bright room in a much larger and much stranger house. There is a passage in Stanislaw Lem's The Magellanic Cloud, the book that inspired a boy in Riga to become an astrophysicist, where the narrator describes the feeling of looking out into interstellar space and realizing that every point of light is a place, that the darkness between the stars is not empty, but merely unvisited. Alexander Kashlinsky spent his career looking past the stars, past the galaxies, past the clusters, past the cosmic web itself, to the faint signals imprinted on the oldest light in the universe, searching for evidence that the darkness beyond the cosmic horizon is not empty either. He may have been wrong about the magnitude or the method. He may have seen a signal that was not there in the WMAP data. But the question he asked turns out to have been exactly the right question. And the universe, through multiple independent messengers, appears to be answering it in a way that will force cosmology to confront the limits of the observable and the meaning of the horizon. We do not know what is out there, but we are finally building the tools to look.